Okay, so off we go. So last time we were talking about some physics applications of Stokes' curl theorem. And so moving along now, I want to remind you all some stuff we talked about in the past. Now everything on the screen at the moment is old news, right? Old news that if you want to test the question of whether a vector field is a gradient, and let me point out we've already made the observation that being a gradient is same as being path independent. So said differently, if you want to test to see if a vector field is path independent, same thing, right? The test for that is to compute Green's operator and see if you get 0. We made an argument as to why this is true, and I won't repeat the whole argument, but the big thing that made it all work was Green's theorem. Green's theorem says, of course, that closed line integrals, in other words, circulations, can be computed as a double integral of Green's operator. Now, again, a bunch of details in here, but this was the thing that held it together, was that circulations can be computed as a double integral of Green's operator. So I stated at the time that, if this is in 3 dimensions, there is no Green's theorem, but there will be this other theorem that's kind of a 3-dimensional version of Green's theorem, and then we'll be able to complete the argument to show that curl is the right sort of substitute in 3 dimensions. Well, here it is, and it is really very much the same argument. It's just where we use, whoops, I didn't quite fit it in there, did I? There we go. Where we use Stokes' theorem in the exact same place where we had used Green's theorem. And notice that everything otherwise pretty much fits the same, right? So if you want to test if a vector, 3-dimensional now, vector field is a gradient, aka if it's path independent, regularity issues ignored. Stokes' theorem is what allows you to relate closed line integrals, namely circulations, to, I'm going to say double integral. Of course, it's a flux integral, but it's a 2-dimensional integral of, well, now curl instead of Green's operator, and that's why the 3-dimensional test here is curl instead of Green's operator. Right? So, like I say, this is just kind of completing a thought. There's no new conclusions on the screen here. This is just showing why a conclusion that we've already drawn, a conclusion that we've already stated, is actually true. Okay. All right. Okay. So, new idea I want to talk about: surface independence. This is a wonderful idea. This is underappreciated. It's certainly under-discussed in multivariable calculus textbooks, in my opinion. There is a case to be made that surface independence is more important than path independence. It depends on how you look at it, and it's an unnecessary question, of course, but I think it's very important, and it's usually not mentioned, which I can't figure. Anyway, let me remind you what path independence is. The idea of path independence is that as long as we fix a starting point and fix an ending point and insist that our curves both start at that starting point and end at that ending point, if you have one such curve whose line integral you're interested in, and another such curve whose line integral you're interested in, there are certain special vector fields called path-independent vector fields where the mere fact of them sharing a starting and ending point will also make them share the values of those line integrals. Right? So it's a really, again, for dramatic purposes, I presented this at the time as, how could this even be true? Surely you're joking. Right? What vector field could possibly, no matter what curve you pick, come on, there's just no way. Right? Dramatic purposes. Alternative rephrase was to realize, now here's just a fact of geometry, if you have 2 curves that start at the same point and end at the same point, then their difference is the boundary of what's in between them. And again, it's just a matter of looking at the geometry, and so this difference, keeping orientations in mind, this says go the correct direction along C1, this says go backwards along C2, okay? Which gives you this orange curve, with this orange curve, of course, being a boundary. Okay? Then path independence is equivalent to saying that closed line integral is 0. So we have sort of two different points of view on path independence. Let me put a check mark right there. Okay, so this is all reminder. Now let's talk about the sort of one dimension up equivalence, sort of analogous thing, and that is surface independence. Let me try to spread this out a little bit. As I go through and sort of color code this, I'm going to try to maintain the color coding pattern so you can see the sort of comparison points. So up here we started with an agreed upon what's going to be our shared starting point and our shared ending point. In other words, we started off with what's going to be our shared boundary for the various curves. Here we are going to again start off with a shared boundary, this time that boundary being a curve, not a pair of points. So one dimension up. And if I have two surfaces that have that correct shared boundary, so S1, if I'm interested in a flux through S1, that being some surface with this shared boundary, and now if I consider, let's see here, S2, if I'm interested in the flux through S2, that also having the same shared boundary. Do be careful with the orientations here. Notice in order for them to have the same boundary, the same shared boundary, I need S1 to be oriented that way, and I need S2 to be oriented that way. So now I'm going to make the outrageous suggestion, again, dramatic purposes, that there are some vector fields, believe it or not, which, as long as any two surfaces have the same boundary curve as in this picture, then you will always get the same flux. And again, it seems outrageous to suggest, right, that these are two totally different surfaces. They share just the most seemingly most trivial of common features, namely the edges are shared. But other than that, totally different surfaces, and yet I'm claiming that they'll always have the same fluxes. Right? Kind of an outrageous suggestion that a vector field could exist that does this. But we will find, actually momentarily, that there's a whole category of vector fields that have this feature of surface independence. Before I show you those vector fields, I'm going to, again, do a rephrase, again, for sort of analogy purposes. Notice that if you have two surfaces, S1 and S2, that have a common boundary, pretend like my hands are these two surfaces. If they have a common boundary, it's like I'm bringing my hands together like this, and like I caught a bug. Right? So that makes an enclosed region. In other words, these two surfaces, by having the same boundary curve between the two of them, they make the boundary of a solid. Right? And again, looking at the orientations, and now notice one's outward, one's inward, and all that. Notice that this thing here that I'm calling S. The difference, in other words, between those two curves is itself the boundary of a solid, and an alternative phrasing then becomes that you can describe surface independence that closed fluxes are always zero. So, as y'all know, I'm a big believer in the idea of patterns, noticing patterns, right? This is a tremendous one. That in the exact same way that there is this shocking notion of path independence that connects up with a bunch of other ideas, as we've previously discussed, there is a highly analogous notion called surface independence as well. Okay. All right, how are we doing so far? Now, again, I've yet to show that any such vector fields exist that have this property. Does everybody see what I'm claiming exists? What the property means? All right, so how do I know that there is such a thing at all? Here's the wonderful insight there. And actually, I do want to sort of erase my mess here. Give me a second. Oh, gosh, I'll do it like this. There we go. Stokes' theorem is actually going to show that every curl field. Okay, regularity issues, yeah, it does have to be continuous. Okay, fine. But every curl field, that noted, is surface independent. So let me show you why this is true, and it's kind of I don't want to say a freebie, but it's a very quick consequence of Stokes' theorem as follows. So let's suppose that my vector field in question here is actually a curl, right? So this is a curl, that is a curl. Right, and let's talk now about my first surface. Here's my first surface, S1. How would I compute the flux through that first surface, S1? Well, let's see here. The flux is a flux of a curl. A flux of a curl? Wait a minute. So where have I heard this phrase before? A flux of a curl. Oh, right. A flux of a curl. Stokes' theorem tells me that I can rewrite that as a circulation. Right? So Stokes' theorem is what allows me to conclude. Let's see. What am I going to do here? I'll use, oh, gosh, I'm running out of colors. I'll use yellow. Stokes' theorem tells me I can compute that green flux as a line integral around this boundary, and of course the boundary, here, still the same boundary. Right, a line integral around that same boundary. Everybody okay so far? Right, again, Stokes' theorem says flux of curl is a circulation of your original vector field. So, all right, now let's talk about the second surface. The second surface, how would I compute its flux? Same vector field. Well, again, it's still a flux of the same vector field, still a curl, right? Flux of a curl. Again, Stokes' theorem. Stokes' theorem tells me I can compute that flux as a circulation around its boundary. And, of course, the whole point is that if it has the same boundary, then that means we're computing this blue integral with the exact same circulation. And so the green integral and the blue integral is computed with the same line integral, and therefore they have the same values. And therefore we have surface independence. Right? It's a lovely little argument. Notice, by the way, it's extremely analogous to an argument that we made about path independence, where it wasn't Stokes' curl theorem, it was the fundamental theorem of line integrals. And again, I think it's a really healthy exercise. Go back in the notes or in the recordings or whatever you work best with, and see how that argument went with the fundamental theorem of line integrals, and how this is a morally equivalent, one dimension up, but otherwise morally equivalent argument. Okay. All right, so neat fact. So this outrageous suggestion that there could possibly be a vector field that is surface independent, namely for which this would always be true, come on, how could that possibly be? Every curl does it. All right. Now, real quick, and again, we're not going to prove this, and it's even harder in this case than the analogous fact for path independence. But not only is every curl surface independent, but regularity issues aside, every surface independent vector field also is a curl. It does go both ways. Again, regularity issues aside. All right, we'll see an example in a minute, but before we can do that example, we need a local test. Y'all remember these local tests? We kind of finished the argument of our curl being a local test of path independence. Now I claim that divergence is a local test for surface independence. So the argument, how does the argument go? Again, totally analogous. My first observation, these conditions are all the same. We just saw that every curl is surface independent, and I claim it goes the other way. I'm not going to show you a proof, but I claim it. We also have seen that surface independence is morally equivalent to saying that all closed fluxes are zero. And now, with these three established as being equivalent, we notice that Gauss's divergence theorem kicks in very nicely, because Gauss's divergence theorem says, oh, closed fluxes? Yeah, boundary fluxes? Right, sure. Boundary fluxes are triple integrals of divergence. Right? And so if the closed fluxes are all zero, these triple integrals of divergence are all zero? Wait a minute, how could all triple integrals, no matter what the solid, every solid, the triple integral is always zero? The only way that's possible is if the integrand is itself zero, and vice versa. So really, really similar argument, and nice punchline. So again, if you find yourself perhaps wondering, can I use surface independence for this calculation? How would I know if my vector field is surface independent? Answer, compute the divergence, see if you get zero. If you do, then yes, you have a surface independent curl field, and go ahead, use surface independence. All right, so let's see an example. Let's get our hands dirty. Here is a question. As I've done before, the very first thing I'm going to say about this question is that notice it doesn't tell you which of your many tools that you could conceivably use should you use. Right? It just says, hey, here's a vector field, here's a surface. Compute the flux. And so you've got to pick through your toolbox and think, okay, well, what are the tools that I know for how to compute fluxes? You can parameterize and plug and chug. That's an option. That wouldn't even be that bad in this case, although there is a much better tool that we're going to use momentarily. But parameterize and plug and chug is kind of I don't want to say default, but it's the unsophisticated, kind of most obvious, I'll say, option. Let's see here. What else could we do? Maybe we could use the divergence theorem. Gauss's divergence theorem. Something to think about. Maybe we could use Stokes's curl theorem. After all, Stokes's curl theorem does say something about fluxes. So maybe, possibly. Right. All right. So I want to eliminate the bad options before I go to the good option here. Right. So first of all, parameterize and plug and chug. It's not that bad, really. You can see it's all polynomials. You can do it if you'd like. I just think it's a little tedious. Plan B at best. Let's talk about the divergence theorem. Why can't we use the divergence theorem? And this comes about by looking at our surface. There's our surface. It's a certain part of this paraboloid. Paraboloids look like this, right? The paraboloid, of course, extends infinitely downward. We only want the part where z is positive, so our paraboloid ends like that. Nevertheless, anyway, there's our surface. Quick observation. This surface, this S, you can look at it. There it is. Picture. It's like an upside-down bowl, and that's not a boundary. Independent of it's got nothing to do with orientation. It doesn't close up. This is not there is no saran wrap underneath this, right? The cereal falls right out. It's an open bowl, upside down, not a boundary. Is everybody cool? Now, a lot of students get this wrong. Very common mistake that students make, because this is where students inadvertently confuse themselves with their own picture. And so it's something to watch out for, and so please do be careful. I've very carefully, as you'll see, not sort of filled in what you might call a whole picture of my surface here, but my surface, it says right here, it's part of the paraboloid. Right? Points along in here, they are not part of the paraboloid. They just aren't. Right? Those points down there are on the plane that I'm using to describe which part of the paraboloid I'm interested in, right? I'm interested in the part of the paraboloid that's above the xy plane, if you will, right? But keep in mind, this business about z greater than or equal to 0, it's just a tool for describing which part of the paraboloid. This does not say S is the union of part of the paraboloid along with, this part of the plane inside of the paraboloid. It just doesn't say that, right? So when you draw your picture, it's very tempting to draw it like this, and then to kind of misinterpret your own picture and think that your surface includes both, the top part, and somehow think that it also includes the bottom part, but it doesn't. Is everybody comfortable with that? I mean, it's easy to misinterpret this. All right. Okay, so Gauss's divergence theorem's off the table. Gauss's divergence theorem's about boundaries. This is not a boundary. Forget about Gauss's divergence theorem. Everybody good? Okay, all right, so let's talk about Stokes' theorem. Why can't we use Stokes' theorem? Stokes' theorem, in fact, does talk about fluxes. Stokes' theorem talks about fluxes of curls. If I were going to use Stokes' theorem on this, I would need to not only know that this is a curl of something, I would need to know what is it a curl of. I would need to find the anti-curl, what I like to call the anti-curl. We don't know how to do that. Finding anti-curls, as it turns out, is algebraically hard. It's not something that I'm going to be able to talk about in this class. So that's kind of effectively off the table as well. All right. So no Gauss, no Stokes, hoping to not have to parameterize and plug and chug. So what are we going to do? And I'm going to use this right here that says, our theorem that we just proved, I'm going to take the divergence, I'm going to see if I get 0, and if I do, then I'm going to infer, hey, I've got a surface-independent vector field here, and I get to change my surface to whatever I want it to be. I've got to keep the same boundary. Shared boundary is critical, part of the definition. But being able to change the surface might really help us a lot. And so here we go. Notice that I can compute the divergence of this vector field. It's easy algebra. The divergence is 0. I get to conclude surface independence. That means that I get to take my curve that I was given, identify the boundary. Looking at the picture, you can see the boundary is going to be that curve right there, this sort of loop-looking thing. That's the boundary. Now I get to pick any surface I want that has this same boundary. Go crazy. Anything you like. If you're want to, you could take that surface. That'd be a weird choice, but you can if you want to. I want to save myself trouble. I want to pick the easiest possible surface, and the easiest surface that I can see in this picture. Now keep in mind, very important rule. It's got to share the same boundary, right? That purple boundary is part of the deal. But look at this nice flat surface right there. Same boundary. I'm just going to throw away my original surface. I'm going to operate now with my new surface, as shown there. And now the problem just got a lot easier. Is everybody on board? Everybody happy? All right. Now, catch, we do have to worry about orientations. right? This is unfortunately very important. And if you look back up here at the picture, when we were first talking about surface independence, I mean, it's weird that this is the case, but if this is your shared boundary oriented that way, and if your original surface is like that, let's just say, right? Remember, the way we relate the surface orientation to its boundary orientation is with the right hand, thumb in the direction of the surface normal, right? Fingers will create a swirl. You see how that swirl side swipes as you kind of drag it further down to closer to where we are, and you see that swirl is going to side swipe that way. Isn't that cool? So when I pick my new surface, let's see here. Okay, well, I will just get rid of that. When I pick my new surface has to be, I have to choose whichever of these orientations is going to make the side swiping thing go the same way. Right? And so in this case, again, it's just a matter of thumbs and swirls and all that. You can persuade yourself that it has to be oriented like so to get the side swipes to work out. That would have our swirls like that. Keep in mind it's kind of going into the page, and so my fingers like that, like this. Does that make sense to everybody? Okay, so we've got to play that same game now. Let's see here, down here. And looking at this picture, notice my original surface was given as oriented downward, like that, which you'd be tempted to call this inward, which, okay, that's reasonable. Thinking now about that, first I've got to figure out what is the orientation on my boundary. I mean, given what my surface is, and again, right hand and thumb in the direction of the given surface normal and the swirl and all that, I say that the swirl goes around like that, and that will side swipe in this direction. So with that in mind, given that this is the orientation on my boundary, and having decided, as I just did, that, I want to use this as my new surface, which way should I orient this new surface? And I have to get it right, and it's a big deal. And again, orientations are, ultimately it's just a minus sign, right? But from a concept point of view, namely what this course is about, this is a sophisticated and critical idea to make the theorem work, is how the orientations work. So please do take this orientation stuff really seriously. It will count for big points on the exam. Yeah.
I know you don't like it when we say like counterclockwise or clockwise rotation.
No. I like it fine. You just have to be clear, right? So as seen from where? That's all.
Yeah. So
yeah.
Looking at like N, if you were to do like the right hand rule, wouldn't it go counterclockwise?
As seen from where?
From the surface.
As well. So you're talking about up here, though, right? Okay. So from up here, like if I were sitting here on the z-axis, where this arrow is pointing right at me, then here, let's just do it like this. Yeah. See, yes, my right hand, if I point my thumb right at me, will appear to be counterclockwise. That's true.
Okay.
Right. So if you want to think about it that way, that's fine. But again, we're currently looking at this from the point of view of outside of the thing, right? And being on the outside, it's going to appear the other way, and that's why it appears. Oh, whoopsie. That's why it appears clockwise as seen from over here, right? But it's one of these deals, right? So you see what I'm saying?
Yeah.
Yeah. Okay. And it is confusing. I quickly, wholeheartedly endorse the statement that, it is confusing, and this is geometrically challenging. And so take your time, think it through, don't whip this out too fast. be careful. It's easy to mess it up. And yes, yeah.
So if you're working from the outside, how are you supposed to orient your hand to get it to curl? Like, because if I'm to the inside, it's curling this way.
Yeah. So
how do I orient it so that I get it?
Yeah. So I mean, one thing you could do is kind of, I mean, it's weird, right? But notice that works, right? So if I point my thumb like that, right, and then I notice that, okay, well, as seen from here, then it appears to be going. From my perspective here, it looks clockwise, and that's why I draw this clockwise. Does that make sense? That's the beautiful thing about the right hand. You can kind of, it's like that, and it just does it for you. Yeah. Okay. Yeah.
Are there situations in which the orientation of like one surface is kind of different from the orientation of another surface? Because it feels like if it's downwards, then it's kind of like that, and it's going like that. So on the surface, you would kind of.
So if you want to invoke surface independence, then come on, man. There we go. Okay. If you want to invoke surface independence, then we do need. We need the same orientation, the same boundary with orientation included. So now, what you may be wondering, tell me if this might help. You look at this picture here, and it's tempting to say that these two surfaces have opposite orientations. One's inward, one's outward.
But they're like both pointing.
But they're also both upward. That's right. So look, and I think this is a really important point, and I would love to spend 15 minutes on the following, but we don't have the 15 minutes. There is no such thing as same or different when you're talking about different surfaces. Right, so I can look at a single surface. I can look at here we go. I can look at just S1 here, and I can talk about on the one hand there's that orientation, on the other hand there's that orientation, and so looking at a single surface, yes, there are two, and they're exact opposites of each other, and you can talk about same and different and stuff like that. But when there's two totally different surfaces, it just doesn't make any sense. Right? And in fact, there's let me just do this with curves so it's easier to draw. Here are two curves. Are they oriented the same or different? I ask rhetorically. And the answer is, well, what a ridiculous question. There's no basis for comparison. They're different curves, for crying out loud. Right? There's no way to actually compare them. Does that make sense? Yeah. Yeah. Okay. All right. So let's go ahead and run this into the end zone on our last question, on the example that we're working on here. In order to make the orientations work out, and by the way, you just have to trial and error this with your new surface. I know which way the direction of the boundary orientation should go. Right? If I want to have the same boundary as I need, if you're going to invoke surface independence, you have to have the same boundary, orientation and all. Apparently I need my boundary orientation to go that way. So let's just try our options. If I orient upward, thumb, fingers, swirl, etc., the swirl goes like that. It's just wrong. So trial and error, my first attempt failed. If I would like to orient S2 upwards, but it gives me the wrong boundary orientation. Okay, so we try again. Attempt number 2. Let's try orienting it downward. And okay, so thumb, fingers, and swirl. Okay, it's going kind of that way, which is correct. And you just got to trial and error it. Is that cool? Everybody happy?
Can you re-explain the first?
What went wrong with the first one?
Yeah.
Yeah. So it's just, so we've agreed that our boundary orientation needs to go that way. So let's suppose that we orient the surface like that. Thumb, fingers, swirl. The swirl goes like that. It's just the wrong way. Yeah. Okay, so orientation established. Now it's just a matter of running it into the end zone. If I can get the thing to work. There we go. So I've got myself a new surface oriented like that. Surface independence tells me that the question I was asked is going to be the same as this question here, namely the flux through the one surface is going to be the same as the flux through my new surface because it's surface independent, and these have the same boundary, orientation and all. And so I no longer have to think about my old flux question. Now I have a brand new surface where life is good. And notice that this dot product is actually really easy to compute. The dot product is just that right there. Now again, you could parameterize and play the parameterization games, but look how easy in this case. Looking at our normal vector 0, 0, 1. I love it when there's zeros. Right, that makes this dot product just super easy to just write down. And my question turns into, conveniently, a scalar surface integral, chock full of symmetries. Integral is equal to 0 by symmetry, and I didn't have to plug and chug. Hardly at all. So this is a really powerful method, right? Surface independence, bonkers powerful. And I'm a big fan, and I wish it were more heavily discussed. Did you have it? Yeah.
Yeah, so can you scroll up just a little bit to the local test?
Yeah. Uh-huh.
So you didn't use the fact that it's surface independence to say that the closed surface integral is 0.
I didn't use this fact, but I did, because the divergence was 0. I did infer from that that surface independence is allowable in the first place. So all this business about changing your surface, that's only for the rare vector fields that are actually surface independent. And so so this part of the argument is very important.
Gotcha. And since it ended up being 0 anyway, is that implying that maybe it was fair for you to use that closed surfaces would be 0 anyway?
No, because this isn't a closed surface.
Okay.
Yeah. No, so again, as you will recall, right? So one of my big themes in this class and any math class I'll ever teach is that there's a dramatic difference between the conclusion and the reasoning, right? And so the fact that the reasoning gets numerically a value that also comes about in a totally different circumstance that doesn't apply here, that's just a coincidence, and the answer just isn't the point, and I couldn't care less about the answer. Right. That's an overstatement. I care very little about the answer. Yeah. How are we doing? Is everybody with me? All right. Okay. I wanted to append something I just said, that, again, surface independence is something that has to be established. You have to know for a reason why it is that your vector field is surface independent. And then to sort of bolster that, I point out that surface independence is rare. And from a certain point of view, it's rare in the sense that the divergence has to be exactly 0. Everywhere. What are the odds, right? That said, vector fields that we deal with in the real world are not a random sample of random vector fields. We deal with vector fields that come about for real reasons. And it turns out that the real world is chock full of vector fields that are surface independent. You still have to check, right? But there are a lot of them. And in your daily experience, this will not be rare. Okay. Alrighty, so we're on to kind of summary stuff now. I'm going to switch over so this is my diagram for R2. Y'all will recall that when we were talking about this, I switched over to my typeset diagram, which I think is easier to read. It's a little bit more sort of full, etc. So likewise for this three-dimensional version of the diagram. And so here we go. I'm going to switch over to that. Again, this document that has this typeset version of the diagram. It has, by the way, it has the two-dimensional version and the three-dimensional version that we'll be working with today. So this is on the website. Right, it's in like the class materials folder or something like that, but it's right there on the class website. So we've now discussed everything on this screen. And so now I want to take a few minutes to talk through the patterns, which are the point, really, of this diagram. Again, where did this diagram come from? It kind of comes from taking an extremely sophisticated collection of ideas, chain complexes and co-chain complexes and stuff like that. Again, way beyond Math219, and kind of boiling off all the rigor and the formality and the scary, right? And just kind of, okay, yeah, but in practice, what does this look like in these very specific scenarios? And so y'all will recognize a lot of this, I think, is, we've already talked about composing these operators in that particular order. It comes out from all the sophisticated stuff we're not gonna discuss. It, I believe, is geometrically pretty satisfying that if you have a three-dimensional region and you take the boundary of that three-dimensional region, you get a two-dimensional, well, I guess that would be a surface now, wouldn't it? Right? You never take the boundary of a three-dimensional thing and get a curve. That's not how boundaries work, right? And likewise, the boundary of a surface is a curve. The boundary of a curve is always a collection of points, etc. So various patterns I want to talk about. First of all, we have our what I call lifetime theorems, and then later I refer to them as local tests. That if you have a gradient field, then the curl is 0, or vice versa. If the curl is 0, then that lets you know that your vector field is a gradient of something. And notice as well, we had an analogous statement. There we go. Analogous statement about curl and divergence. In fact, we just established, just today, this local test. If the divergence is 0, that tells you that your vector field is a curl, aka is surface independent. Okay. All right, let's see. Let me kill that. Let's see here. Oh, we talked about the pattern. We talked about the two-dimensional version of this, but the pattern of the various theorems. So, for example, if you take a gradient of a function and then look at the boundary of a curve, then plugging in those boundary points into the original function, taking the line integral of the gradient over the original curve, you get the same thing both ways, right? So there's a little diagrammatic pattern that we see there for the fundamental theorem of line integrals. And I like to point out, you might have noticed this already, but Gauss's divergence theorem, same pattern. With Gauss's divergence theorem, it's a vector field of which I take the divergence. It's a solid of which I take the boundary surface. But same conclusion, that the flux of the original vector field through the boundary surface, the triple integral of the divergence over the original solid are the same. It's the exact same pattern. And likewise for Stokes's curl theorem, same exact pattern. So this is super useful for students learning the material because you don't have to memorize 3 separate theorems. You have to know the pattern. Right? If you have this diagram in your mind, then simply understanding the pattern will allow you to have all 3 of the theorems memorized. So I think that's pretty cool. All right, last thing I want to point out, and again, there's just so many patterns that are on this diagram, in effect. We talked about some special vector fields. Not all vector fields, but there are special vector fields which have several different properties. Those several different properties of which show up on this diagram in certain ways. So on the one hand, I'm talking about vector fields that are gradients of an actual function. So gradient fields. Right? On the other hand, These same vector fields, when you take the curl, you get 0. Namely, they are irrotational. Keep in mind, curl describes how things are kind of rotating. And if you get 0, irrotational. Makes sense. Which we also saw are path independent. Namely, any two curves with the same boundary points will give you the same value for the line integral. Okay, so now again, we've talked about that little, sort of diagrammatic representation. And again, I'm a big believer in noticing patterns. There is a tremendous pattern between path independence and surface independence. As follows. This pattern relating having an antigradient, curl being 0, being path independent, the exact same pattern holds one dimension up. Exact same pattern. There are special vector fields that are curls of something for which divergence is 0, which are surface independent, namely two surfaces with the same boundary curve gives you the same flux, right? So the pattern describing the special features of the special vector fields here is the exact same pattern that describes the special features of the special vector fields here. And I think that is awesome. I mean, the coincidence, seeming coincidence of it all, right? What are the odds? And again, useful for you. You don't have to memorize two different sets of rules, right? That, oh, wait, if I want to know if it's a gradient, wait, oh, shoot, was it curl or was it divergence? Oh, gosh, which one is it? You don't have to remember that. If you have the pattern, if you have the diagram in your head, you just remember one set of patterns, right? And then, okay, well, let's see. If I have a vector field and I want to know if it's surface independent, okay, well, then apparently, thank you, diagram. Apparently, I'm supposed to take the divergence and see if I get 0. Pattern does the remembering for you. Is that cool? Yeah.
Are we going to get like this on the exam?
No, thank you for the question, though. That's good. It brings me to a point I want to make, and this is going to sound outrageous, but here we go. I encourage you all to memorize this diagram, and I know that sounds like a lot, but here's the thing. I betcha some of you have, in fact, already accidentally memorized this diagram because it's so full of patterns. There's so much to it, right? What else have we done on three-dimensional domains? Well, triple integrals. That's what else? What else would be here on a three-dimensional domain, right? What else has been involved in our discussions about, for one-dimensional curves? Well, vector line integrals. That's the only thing that's come up, right, in our discussions of all this stuff. So the one thing you do have to memorize, and there's just no way around this, is you do have to memorize which order these go in. You can't sort of like reason your way through that quite, right? But make sure to memorize gradient, curl, divergence. Okay? GCD, if that helps. I don't know what. But once you have that memorized, it's all patterns at that point. And just sort of like, well, what else could it be? Kind of things. So I think a really good check, a really good test would be to stare at this diagram all you want, right? Look it over, think through, okay, what do I need on here? What's really happening on here? And then put it away, clean sheet of paper, see if you can reproduce it. I'll bet you can. It's not that bad. Does that make sense? Is everybody good with that? A lot of students, by the way, like to, on exam 3 or the final exam, like to very first thing they turn over the cover sheet, and as soon as the go happens, they turn over the cover sheet and write out the diagram, and then they have a copy of the diagram to work with. It's like bringing your own cheat sheet. Right? Something to think about. Okay. All right, let's see here. Back to the notes here. We've just done all of this. I, as expected, kind of ran out of time for non-essential, optional stuff that I wanted to be able to do. What follows is just a bunch of examples, right? There's kind of a big picture sort of strategy for how to use the diagram, how to make reasonable decisions. And then I have here 6 examples of putting these ideas in action. And so while I won't be able to go through those in class because we're out of time, what I will do is give y'all the recordings where I've discussed all 6 of these examples in great detail, and I will put those up on the YouTube channel this afternoon when I'm uploading today's lectures. And y'all can, you don't have to, right? It's highly optional. It's just examples, but I encourage you to look through and listen to that. If you want to listen at double speed, I get it, right? But see how we use the diagram to solve problems. And talk to me after class because I think we're out of time.
No, yeah, you already answered what you were saying.
Perfect. Okay, all right. See y'all later. Have a good one. Chapter 4 tomorrow, or Wednesday.
Sorry, where on your YouTube channel?